Hello, AP Physics students. We're going to do another example problem here. We are going to be checking out problem number 48 from chapter number 4. All right, let's make sure we can see that on the screen there. There we go. All right, so here we go. It says I have two crates, one of mass 75 kilograms, one of 110. They're in contact on at rest on a horizontal surface. A 620 Newton force is exerted on the first crate. If the coefficient of friction is 0.15, calculate the acceleration of the system and the force the crate exerts on each other. Okay, well, just a ton of information here. So let's go ahead and get started. Okay, let's get a picture and a free body diagram here. So I have two crates. Right? I'm going to call them M1 and M2, okay? Close enough. So, and just to keep things straight, I'm going to write this out here. M1 is 75 kilograms and M2 is 110 kilograms. Okay, what else do I know? Well, let's do some free body diagrams here. It looks like I'm exerting a force F on crate M1, and that force is 620 newtons. By the way, I'm establishing my x-axis as being positive and to the right. What else do I know? I know the coefficient of kinetic friction is 0.15, so that's good information to write down. All right. And then the first question I want to know is, what is the acceleration of the system? Okay. So what is A? That's what I want to know. Okay, here's the hint that I think works really well. If you have two boxes or two objects that are connected and they stay connected throughout the entire problem and they're not separating or anything like that, you can really just think of them as one big object, okay? So I'm just going to kind of redraw this and think about this like this. I have a single box of mass capital M, which is M1 plus M2, which is 185 kilograms, right? I'm applying this force F. What's its acceleration? That's an easier problem, and it's essentially the same. I mean, if these boxes were glued together, we wouldn't know the difference. So yeah, that's the problem I'm going to solve here. And since, like I say, since they don't separate, I can do that. So I have the weight pointing down, I have a normal force, and I have a force of friction, and find the acceleration. Well, that shouldn't be too bad, right? Let's write out some things I know here. The weight would be equal to capital M, 185 times G, 9.8. So I could figure out what the weight of this guy was. It would be 1,813 newtons, okay? Now, in this case, the normal force should be equal to the weight, equal in magnitude, opposite in direction, okay? So I also know what the normal force is. What's the friction force? Well, the friction force should be equal to the coefficient of kinetic friction times the normal force, right? So I could plug in my mu, 0.15, and my normal force and get a number for my friction force. That should be 272 newtons, all right? Well, with all of this information, I should be able to figure out the acceleration of my box using Newton's second law. So the acceleration should be the net force divided by the mass, net force being a plus F, the 620 Newton force to the right, so it's positive, minus the force of friction divided by the mass of the box, right? So this ends up being 620 minus 272 divided by 185. And if I do my algebra here, I get an acceleration of a plus 1.88 meters per second squared. All right? And that is my answer to part A. All right? Again, big idea here. If two objects are connected and staying connected, Just treat them like one object and do Newton's second law. So that's part A. Okay, let's take a look at part B up here, okay? Part B gets a little trickier, okay? So for part B, I am going to need a full two-box free body diagram, okay? So in part B, I need to figure out the contact force, or how much force is box 1 pushing on box 2 with, okay? So we're going to need full free body diagrams here. So again, on box 1, I'm pushing to the right with some force F, right? Each of these have a weight. I would call this W2. I would call this N2. I could call this N1 and this W1, all right? And then each box has a friction force pointing to the left, right? Force of friction on box 1, force of friction on box 2. Now, here's what's new. These boxes are pushing on each other. How are they pushing on each other? Well, box 1 is pushing on box 2. I'm going to call that force F sub 1, 2. But then by Newton's third law, if box 1 is pushing on box 2 must be pushing on box 1 with a force equal in magnitude and opposite in direction. So 1 pushes on 2 to the right, 2 pushes back on 1 to the left. Again, that's just one force, an interaction between two objects. All right. So let's look at here box 1. For box 1, the acceleration of box 1 should be the net force acting on box 1 divided by the mass of box 1. Well, what is the net force acting on box 1? Well, the normal and the weight should cancel each other out, right? So really the forces I have is a plus F to the right, the 620 Newton force that I'm pushing on it originally with, right? And then I have minus a force of friction, right? Again, you know, to the right is assumed to be our plus direction. So this force of friction is pointing to the left. And then I also have the force that box 2 is pushing on box 1 with, okay? All right. Well, let's see what I know here. I do know the acceleration of box 1. As we showed before, box 1 is accelerating as the system is at 1.88 meters per second squared. So I know A. I know mass. I know this force. I should be able to figure out the friction force on box 1, right? That would be mu sub k times the normal force on 1. Okay, and if I figure that out, that would be mu sub k m1g, which would be 110 newtons. Again, I'm plugging in here 0.15 and 75 and 9.8. All right. So the only thing I don't know in this equation is F21. Well, that's what I want to know. How much force is box 1 and 2 exerting on each other, right? What is that? What is that force? Well, if that's the only thing I don't know, I can solve for it. Okay, so if I plug this in, what is A1 plus 1.88? What is F plus 620? What is the force of friction minus 110? What is F21? I don't know, but I will soon. Divided by 75. Okay, so that is the equation I can use to solve for the force of interaction between box 1 and box 2. Okay, so if I do a little algebra here, I get 142.5. I'm going to multiply by 75 on each side. Okay, 142.5 equals 620 minus 110 minus F sub 21 minus 368.5 equals minus F21. Skipping a couple steps here, and F sub 21 is equal to a plus 368.5 newtons. So this is how much force box box 1 is exerting on box 2 to the right, and conversely, how much force box 2 is exerting back on box 1. So that's my force of interaction between the two boxes, sometimes called a contact force. In part C, though, it says, what if the boxes were reversed? What if I had the big box first and then the little box and they were touching? That is an interesting problem that I am going to let you work out for yourself following this example up here. So, nice work, physicists. Work out that final step for part C. And as you're doing that, you can look longingly at this beautiful photo of, look at that, the cross-country running team. Oh, how about, oh, look at there's Jack Graves, good-looking guy. All right, where's Nikola? Nikola's in here somewhere. Yes, Jack Graves, or Jack Kokinen. Where's Jack? He's in there. We got to embarrass him some. Oh, where'd you go, Jack? Where did you go? That's Coach. There's Jack looking off into the distance. Of course, Coach Kirsten is in there. And of course, the Shermans, Matt Sherman, Mike Sherman, right there. So what a good-looking cross-country running crew. So, all right, nice job, physicists. Carry on.